Hi viewers, welcome to another tutorial class on mechanics of materials. In today's class, I'll explain another problem on stepped bar. Let us start. Determine the maximum axial stress developed, the ratio of maximum stress to minimum stress, and the deformation produced in a stepped bar shown in figure. Here we have a step bar fixed at left end and it consists of three uniform cross sections. First section is with the cross sectional area A and Young's modulus E. Second section have a cross section area 4A and Young's modulus 2E. And third portion D having a cross sectional area A and Young's modulus E by 2. The A and D values are given and the length of the first portion AB is L, and here BD is also L, but at C there is another force acting. So even though the area of cross section is uniform for the section BD, we need to consider this as two different portions, BC and CD, and this is because an intermediate load is coming at C. And the last section D is having a length L, and L is given as 1000. So first section AB is 1000 mm, BC is L by 2, that is 500 mm, and here CD is again 500 mm and D is 1000 mm. Area and Young's modulus also correspondingly we can find out. Let us find out the forces in the various sections. In the first section, the forces acting right side to this section. Okay, beyond the section, whatever forces are there, we will sum up. Let us sum up the forces beyond that section considered. So here you have minus P because it's leftward minus, and this is plus 2P, and here it is plus 2P. So these two forces are acting rightward, so plus, and this is acting leftward, so minus. So summing up, you will get 3P, and we know that P is 10 kilonewton. We are given that P is 10 kilonewton, so 3P is 30 kilonewton. Now let us take a section between the portion B and C. So when you take this section, you have to consider the force at C, it is 2P, and here at E we have 2P force. So both are acting rightward. So 2P plus 2P will get 4P, and P is 10 kilonewton, so 4P is 40 kilonewton. We will not consider the forces on left side. Okay, so wherever you take the section, only the right side portion is considered, and we take rightward as positive and leftward as negative. So both the forces are acting in the positive direction, so you take 2P and 2P, so it is 4P, 40 kilonewton. Now when you go for the section CD, the forces acting right side of the section, that is only 2P. The force acting at C will not be considered because we are taking a section between C and D. The force which is acting at C cannot be considered. Now the force is 2P, it is 20 kilonewton. In the last section, that is DE, again we can see only one force, 2P, which is 20 kilonewton. Now let us tabulate the data. The force in the first section, we got it as 30 kilonewton. It is 30 into 10 raised to 3 Newton, since each kilonewton is 1000 Newton. And the second section we have 40 kilonewton, so that is 40 into 10 raised to 3 Newton. And third section we have 20 kilonewton, that is 20 into 10 raised to 3. And fourth section 20 kilonewton, 20 into 10 raised to 3. L1 is given as L. L is 1000 mm, so directly I have taken 1000 mm. L2 is L by 2, which is 500 mm, and L3 is also L by 2, which is again 1000 by 2, 500 mm. L4 is L 1000 mm. Now A1 is first section we have area A. A is 400 mm square. A is given as 400 mm square. So A1 is 400 mm square. A2 and A3 are same, and which has the area 4A. So 4A is 4 into 400, 1600 mm square. So A2 is 1600 and A3 is also 1600. So both are having same area, but you are considering it separate sections because an intermediate force is acting at C. Now A4 is A, which is 400 mm square. Similarly, you can find out E1. E1 is E, which is 105 gigapascal. 105 gigapascal we have to convert by multiplying by 10 raised to 3. It will give Newton per mm square. Now E2 is twice the Young's modulus E. E is 105, 2 is 210. Okay, 105 into 2, 210 gigapascal, that is 210 into 10 raised to 3 Newton per mm square. Now E3 is also same. E3 is for the portion CD. So E3 is also 210 gigapascal. Now E4, the last section, you have E by 2. Young's modulus is E by 2, half of this. So that will be 52.5 gigapascal, or 52.5 into 10 raised to 3 Newton per mm square. So we got the data for all the 4 sections. So this is first section. AB is first section, BC is second section, and CD is third, and D is fourth section. So all the data is tabulated here. Now let us find out the stress induced in various sections. First section, we have stress is sigma 1 P1 by A1. The force is known. Force is 30 kilonewton, 30 into 10 raised to 3 Newton, divided by area is 400, which will give the stress as 75 Newton per mm square. In second section, we have 4P as a load. So 4P is 40 kilonewton, 40 into 10 raised to 3, and the area is 4A, which is 1600 mm square. We have already tabulated this force and area. Now 40 into 10 raised to 3 divided by 1600, which will give 25 Newton per mm square. So stress in the portion BC is 25 Newton per mm square. Now for the section CD, the stress is different because the load will vary. Even the area is same and Young's modulus is also same, but the load will change in the portion CD. So stress is going to be different there, and sigma 3 is P3 by A3. And the load is only 20 kilonewton, that is 20 into 10 raised to 3 Newton, divided by the area is 1600 mm square, so which will give the stress as 12.5 Newton per mm square. Now the last portion DE, the stress is P4 by F4, and P4 is 20 kilonewton, 20 into 10 raised to 3 divided by area is 400 mm square, so which will give the stress as 50 Newton per mm square. So we got the stresses in all the 4 sections. Now we can find out the maximum stress. Out of these 4 values, maximum values 75 Newton per mm square, which is happening in the first section, that is in the portion AB. And minimum value is coming in the section 3, that is for the portion CD. Their minimum stress is acting 12.5 Newton per mm square. So we have identified the maximum stress and minimum stress. Now you can find out the ratio of this maximum to minimum stress. So maximum stress is 75 Newton per mm square. So I given by a subscript max, and minimum stress is 12.5 Newton per mm square. Now the ratio of this maximum to minimum you can find out. That is a part of the question. So 75 by 12.5, which will give 6. So the ratio of maximum to minimum stress is 6. All materials are different. There are 3 different materials. So even though this is maximum, other portions can fail. Say maybe the last section can fail. That material cannot withstand that 50 Newton per mm square. That portion is likely to fail. Anyway, we have identified the maximum and minimum stress and found out the ratio of maximum to minimum stress. Now let us find out the total change in length. So we can find out the change in length in the individual sections by applying the formula of delta L1 is equal to P1 L1 divided by A1 E1. We identified that forces and other material properties. We have tabulated all these forces, length, area and Young's modulus, 4 different sections. Now you can substitute that P1 is 30 kilonewton, that is 30 into 10 raised to 3 Newton, and L1 is 1000 mm, A1 is 400 mm square, and Young's modulus is 105 gigapascal, which is 105 into 10 raised to 3 Newton per mm square. So which will give 0.7143 mm. Similarly, you can find out delta L2. Force is 40 kilonewton, 40 into 10 raised to 3. L2 is L by 2, which is 500 mm, and area is 4A. So 4 into 400 you will get 1600, and Young's modulus is 2 times E, and E is 105 gigapascal, so 2 times E is 210 gigapascal, 210 into 10 raised to 3 Newton per mm square. Substituting you will get 0.0595 mm. Now delta L3 is P3 L3 divided by A3 E3. P3 is 20 kilonewton or 20 into 10 raised to 3. Length is L by 2, 500 mm. Area is 4A, 4 into 400, 1600. Young's modulus 2E, that is 2 into 105 gigapascal. So you get 210 gigapascal, 210 into 10 raised to 3 Newton per mm square. So it works out to 0.02976 mm. Now delta L4 is P4 L4 divided by A4 E4. P4 is 20 kilonewton or 20 into 10 raised to 3 Newton, and L4 is equal to L, so 1000 mm. Area is A, 400 mm square, and Young's modulus is E by 2. E is 105 gigapascal, so E by 2 is 52.5 gigapascal, so 52.5 into 10 raised to 3 Newton per mm square, which gives 0.9524 mm. Now summing up all these 4 deformations, all are tensile forces, so tensile stresses are induced, and correspondingly we got all increase in length. So these 4 deformations all are increase in length. So we can add all these, which will give the total change in length. So delta L is delta L1 plus delta L2 plus delta L3 plus delta L4. The summation of all the 4 values will give the total change in length is 1.756 mm. So this is the deformation produced in the stepped bar. So there will be an increase in length of 1.756 mm. That's all for today. Thank you for watching.